like to invite to the podium Dr. Yannis Yannoulis. He is at postdoctoral at the National Technical University of Athens and team leader of the Photonics Communication Research Laboratory on the design and development of novel optical systems for quantum communication. Yannis, the floor is yours, and he will do the first lecture on the QKD architecture. Thank you.
Thank you, Leah, for the nice introduction. So, let's start to give you the context of my today's talk. I can start from a slide that Harris has presented previously about the system of architecture of the prepare and measure QKD. What is, as Harris mentioned previously, a QKD is a communication between two parties, Alice and Bob, including both classical channel and quantum channel, and the goal of this communication between the two parties is to exchange, to distill secret keys, symmetric keys, in order to be used for symmetric encryption, which is the case for my talk today, to focus on the quantum channel, on the quantum links, which are the principles and how we can implement the quantum layer for the QKD system. Let's start a few words. The BB84, you have already heard about this protocol. This is the reference, the certified, the standard protocol for the quantum key distribution. A few words about this protocol in order to introduce you in the slides that will be following later. In this protocol, the BB84, the two parties, Alice, the center station, and both the receiver stations, randomly select two different bases, the X base and the Z base, in order to encode in 1 degree of freedom, for example, in the polarization, the quantum information of the photons. In this exchange between the two Alice and Bob parties, if both parties agree on the same preparation and measurement base, as you can see on the photon-based alignment on the polarization on the lower scale of this figure, these qubits can be registered as bit keys, as valid keys for the quantum key that will be created. When Alice and Bob use different base, for example, Alice prepare qubits in the X base and Bob measure in the Z base, as we can see later on, the qubits, then these register clicks cannot be used and they will not be part of the symmetric key. At the end, the key sequence, as you can see in the last row of this figure, is the final key that has been distilled and can be used and can be securely used for the needs of the symmetric encryption. One important point, and this is the message I need to keep from this slide, for the QKD, instead of using some assumptions for the computational power of the anyone eavesdropper, the quantum security guarantees that the key will be securely exchanged just by the laws of the physics, just by computing some probabilities following the principles and the layers of the quantum mechanics that tell us that no one has eavesdropped this channel. Let's zoom in this layer of the BB84. An alternative approach how we can define the BB84 in terms of its principle. 3 different principles. We need to have a random generation and a random selection of bases. This is the point where we need the quantum random number generation, the first block. The second block, mutually unbiased bases to create in the physical qubits, as we can see later, this very important algebra operation of mutually unbiased bases. And why we are protected in the quantum era? Because we exchange quantum objects, single photons, so the no-cloning theorem is there. No one can copy the unknown quantum state of each photon. So this is the third principle that guarantees the security of the QKD. Let's start just one slide for the QRNG. In the previous training, Kostas Versokinos presented thoroughly some information about the QRNG. The randomness in the quantum world is the true randomness. Don't leave random numbers to chance is the motto of the quantum people. This means that we need quantum engines in order to generate true random numbers. A simple implementation of these true random numbers is to create quantum objects single photons, Fock states, following the quantum mechanical formalism, and use one photon, one quantum state, entering one unbiased beam splitter, 50-50 beam splitter. The probability of the photon exiting the ports of the beam splitter is equal and truly random. This is a simple implementation of QRNG and the one that the theory of QRNG starts with. In many QKD systems, of course, there are alternative implementations with a lot of advantages and implementation challenges. Let's start with the second block, with the mutually unbiased basis. Start a few words about the formalists. I think that most of you, the young students and the junior researchers, are familiar with this formalism, the Dirac notations. We use two main bases in the QKD. When you operate a QKD system, you will see the X base and the Z base. Actually, these are the two Pauli matrices, and these are the eigenvectors of these Pauli matrices, which implement the computational basis. The first one, working in the Z basis, the black arrows, as you can see. So this is the eigenvectors. And also, if we rotate the base, speaking the language of algebra, we would take the X basis, which is a quarter rotated base. Why we need these two different computational bases in our protocol implementation? Because if we prepare the photonic qubits in one base and we measure the photonic qubit in another base or in the same measure on the Bob station which the Alice has prepared the photonic qubits, we will take completely different results. Let's start with the first case. Alice, the center station, prepare its photonic qubits in the Z basis, and also Bob perform the measurements in the Z basis. The outcomes of this measurement result will be totally 100% sure about the outcome of their measurement. When we project the state on the one or the other measurement, we will take 100% of the outcome results. When we prepare in the Z basis on the Alice station and we measure in the X basis on the Bob station, as we can see on the second part of the calculations, the outcome of this projection, the outcome of these measurements in our QKD will be completely random. We will take 50% in the outcome of the results. And why this result is important in our case? Because these probabilities guarantee that if some eavesdropper take an attack in our link, measure the photonic qubits, and prepare on the same measurement base its qubits to be sent on the Bob station, then with some calculation that goes beyond the needs of this presentation, the qubit, the error rates, can be easily detected from the Bob station. So this uncertainty, which is something that has been already described, between the two Pauli matrices, this is the well-known commutator, the non-zero commutator between the two Pauli matrices, is the core part of the mutually unbiased basis. This is the story of the algebra of the quantum mechanics. Let's go from the Hilbert space to the physical lab, to the physical qubits. We need to encode these properties in actual photons. So we need to transfer our way of implementation from Hilbert space to photonic qubits. What we need, as you can see, to translate this computational basis in actional states of the photons. So in an easy implementation, we can take the 0 and 1 in the Z basis, computational basis, as the horizontal and vertical polarization of the photon. We can take the 0 and 1 of the X basis, computational basis, as the diagonal and anti-diagonal base. This result will give us the opportunity to create the probability, the uncertainties that have been already described in the previous calculations. So the challenge and the quantum engineered part, and this is something that we are working in the laboratory, is to find efficient optical hardware that give us the opportunity to encode this mutually unbiased basis. Let's take an example. an example that is at the core of the optical engine of the QKD systems that are also part of the Hellas QKD architecture. Polarization encoding, how we can generate these two mutual unbiased bases. We can take just a one Sagnac type interferometer, and by controlling the phase modulator within the Sagnac loop, we can generate two different mutually unbiased bases. The first one, by controlling the phase difference between 0 and pi, we can take the diagonal and anti-diagonal base, and by introducing pi, half pi, and 270 degrees phase control, we can take the circular polarization orthogonal base. In this way, in an easy way and robust way, as it has been proven experimentally, we can generate actual or mutually unbiased bases in a robust way in an encoded qubits. This is just one example of encoding. Just to give you an idea in the context of encoding in the Hellas QCI, the thin quantum system, I suppose that Simone will present some details on that, has this polarization encoding. In our architecture, we have also some Clavis QKD systems that they can use a different encoding scheme, a way for implementing the Hilbert space in the photonic qubits by using time-bin encoding and also exploiting the phase relation between some states on the implementation. This is actually the QKD systems that have been involved in the overall Hellas QCI architecture. And coming to the third pillar of the security of the QKD, who guarantees that no one can clone the unknown state during the exchange? The no-cloning theorem. This is one of the pillars of the quantum mechanics. Of course, you can easily check the reference textbook of Stefanos Trachanas provides a really nice material for the background of this no-cloning theorem for the young students from the Greek universities. The linearity of quantum mechanics is here and guarantees this property. Challenge from the theory of quantum mechanics to the implementation in the laboratory. We discuss about single photons. We need to generate quantum object as single photons. It's not an easy task. Going from Fock state, an ideal quantum state, to the single photon, it's not an easy task by using attenuating lasers. This is something that my colleagues Argyris and Aris will discuss in detail tomorrow, how we can generate single photon pulses, how you can implement these pulses in the laboratory and validate the properties, the statistical properties of these pulses in the laboratory. As you can see, one of the main challenges is the Poissonian distribution that kills, let's say, the quantum object, since it introduces some uncertainty of the coherent line in the statistics. But more details will be following tomorrow by my colleagues. And we come to the third, let's say, a key metric for the QKD system. If you will have tomorrow the opportunity to check the QMBER in the QKD system that have been already installed as the key metric of the QKD systems. The quantum bit error rate, the error rate that works in the QKD, which is the definition, the quality of the preparation and the analysis of these orthogonal states. As you can see from this formula, when we measure the QMBER, we measure the error counts, the counts that we do not expect, as part of the sum of the counts that are registered on the single photon counters. This is the definition of the QMBER. And which QMBER values are acceptable when we operate in one QKD system, one QKD links? We have a fundamental limitation from the information theory. We need to have positive security rate, so coming from this inequality, we can take at least, by taking some assumptions, and 11% of quantum bit error rate. In practical QKD systems, we need to lower the quantum bit error rate, the error rate of our system, just below the 10% and even lower in order to have sufficient security rate generation and keys to be used for our application. And we come to the question, why this? How, before starting to the question how we can measure the quantum bit error rate. Hannes, in one slide before in his presentation, mentioned that this method it's not secure. Of course, there is a side channel loophole. We generate a programmable pattern with two polarization states and a state order of programmable polarization. Of course, it's not a secure partner, path to exchange a key. Someone can detect the pattern easily, but it allows us to calculate in an easy way the QBER in the laboratory. So we generate on the early station this pattern. At the odd time windows, we have the horizontal polarization. At the even time windows, the vertical polarization. And on the receiver station, on the polarization analysis, we just measure the rates of the error counts. In this way, we can easily calculate in the Z basis the QBER that is the QBER of our system. And we're coming to the last part of our discussion, which is the origin of this quantum bit error rate. We are working in the laboratory with true components, which have imperfections, so what we design in the Hilbert space cannot be reflected in an ideal way in the laboratory. For example, in the polarization, when we consider some perfectly orthogonal state, when we fabricate this polarizer, we can check on the right part of this figure that are not ideally orthogonal. This means that non-ideal polarization extinction ratio contributes to a significant quantum bit error rate. This is actually the intrinsic qubit quantum bit error rate. Another case that we need to tackle in the research implementation, the lab implementation, is the polarization basis rotation. You can easily check the basis as abstract basis in the algebra, but in the laboratory you have rotated basis, so you need to adjust continuously the drift mitigation and compensate the drift mitigation in order to take the measurement on the right basis. This is actually the basis rotation and the quantum bit error rate that is directly linked with this basis rotation. As you can easily check, this is the standard formula of rotation matrix that is applied in order to take the rotation of the reference frame for the polarization in our measurement station. And coming to the last part of the deployment, when we have noisy channels, not only the imperfection of the systems are there, but also noisy background photons from another sources of errors. This is the final formula of quantum bit error rate that also my colleagues tomorrow will give you an anatomy of this formula and the way that all the sources of these noise sources are part of the implementation. We have non-ideal detectors. We have clicks, register counts. We are not part of the detection of a photon, but error detection in the SPAD, in the single photon detector. We have also photons from another sources, for example, solar radiance, when we implement satellite wireless links. When we have in the same fiber classical channel generate Raman noise photon due to the spontaneous Raman scattering. So this part is also contributing a significant number of noise photons, and all these sources contribute to a drastic and significant increase of the quantum bit error rate. And what we can do in order to mitigate and take some countermeasure, the motto, the experimental discussion we have in every coexistent experiment with my colleagues is to close the window to the QKD channel. Which means that we need to have spectral domain filtering to isolate spectrally the detected single photons for the QKD by using narrow filters and also notch filter to remove the classical background noise, to have temporal filters that are closed window, temporally narrow filters in order to detect in a narrow temporal window the detected photons, and also in the spatial domain to couple the radiation in the single mode of fiber, for example in the satellite QKD links, in order to block the background noise using this method. This is more or less the idea and the strategy for lowering the quantum bit error rate in practical QKD system. With this slide, I think that I have finished, and this is the information of my colleagues that tomorrow will provide you more information, details about parts of this presentation. Thank you.